So when we have a weak base reacting with water, we know that it's going to steal an H plus and produce hydroxide, and then a conjugate acid or a balancing entity. So it doesn't matter what that conjugate acid is, because those are both going to be always on a 1-to-1 ratio. So we can simplify it, and rather than have OH times the conjugate acid, just call it OH squared, divided by weak base minus the change in concentration. So remember, with the acids, that change is usually so small that we can typically ignore it. So we can simplify this equation to Kb equals hydroxide squared divided by concentration of the weak base. So if we can recall from the last lesson, the Ka values for most weak acids are provided in your data book on page 8-9, but the Kb values for the bases are not provided. But we can use this equation to solve for it. So we take the Kw value, which is 1 times 10 to the minus 14, and then divide it by Ka of the conjugate acid. So if we look at an example, if we find the Kb for ammonia, we can locate ammonia in the data book on page 8-9. So we're looking up that value and using the conjugate acid value. So if we look up the ammonium ion, so the value for the ammonium ion is 5.6 times 10 to the minus 10. So that's the value that we're going to substitute in to our equation. So 5.6 times 10 to the minus 10 is the Ka. And if we divide Kw by Ka, we get a Kb value of 1.8 times 10 to the minus 5. Calculate the Kb for potassium hydrogen sulfite. So potassium hydrogen sulfite is an ionic compound, which means that in solution it's going to dissociate to potassium and hydrogen sulfite. So the potassium's a spectator, but the hydrogen sulfite is going to act like our weak base. You have to be careful when you're dealing with these amphiprotic substances because they can act like an acid or a base. So when you're looking up the Ka value of the conjugate acid, you want to make sure that you're looking in the column on the right to find that substance, because you're going to see it twice in the data book. So if we look on page 8-9, potassium or hydrogen sulfite can be found in two different places on. So if we look on this side, we can find the hydrogen sulfite here, or scroll down a little bit further and we find it here. So which Ka value are we going to use? Because we're solving for Kb, the hydrogen sulfite is acting like a base, so it's really important that you locate it on the column in the right, in where the bases are found. So we're going to use this Ka value, not the 6.3 times 10 to the minus 8. So it's really important with those amphiprotic substances that you be careful which Ka you're using to solve. So the value that we want is 1.4 times 10 to the minus 2. So that's what we'll sub in to solve for the Kb. So Kb equals 1.0 times 10 to the minus 14 divided by 1.4 times 10 to the minus 2, 7.14 times 10 to the minus 13. So this is the value that we're going to substitute in if you were setting up an expression for Kb. So again, we can simplify this with the Kb expression. If the change is very small, which usually it is, so if the weak base has a concentration more than 1,000 times the Kb value, then we can eliminate that change and simplify the Kb expression. So hydroxide squared divided by the concentration of the weak base. If we rearrange that to isolate for the hydroxide concentration, then we get Kb times weak base and take the square root of that. So if we look at an example, Calculate the percent ionization, pH, and pOH of a 1.5 mole per liter solution of sodium acetate. So first of all, let's write out that formula for sodium acetate. This is an ionic compound, so what will happen is it will separate into the two ions. So we get sodium and an acetate ion. So the sodium's a spectator. It'll be the acetate that's going to react with water to produce hydroxide and our conjugate acid, which is acetic acid. We don't have to include water in the ice table because liquid water is never included in an equilibrium expression. So let's go to the data book then and see which Ka value we're going to use to solve for Kb. So we need Kw over Ka of the conjugate acid. So if we're looking in the data book, we're looking for the acetate ion. And remember, it's a base, so we're looking in the row on the right. And you'll find it right here. So the Ka of our conjugate acid is 1.8 times 10 to the minus 5. So that's what we're going to sub in to find that Kb value. So we have Kw is 1.0 times 10 to the minus 14 divided by the Ka value, which is 1.8 times 10 to the minus 5. So we get 5.56 times 10 to the minus 10. So here's our Kb value. What information do we have is the concentration of our solute of the sodium acetate. So this is a 1-to-1 ratio, so the concentration of our acetate ion will be equal to that. We can assume that the hydroxide and the acetic acid start at 0, and I want to know the pH, pOH, and percent ionization. So ultimately, we have to solve for this hydroxide concentration. I don't know what those are going to increase by, so we can call it X, and here will be minus X. If we take our Kb and divide the concentration of the acid by that Kb value, so 1.50 divided by Kb, we get a number that's much greater than 1,000. So we can ignore this change here. So if we set up the Kb expression, we have OH squared divided by concentration of the weak base. Our Kb is 5.56 times 10 to the minus 10 times x squared over 1.50. So if we rearrange this to solve for the x, multiply both sides by 1.5 and take the square root. We get x equal to 2.89 times 10 to the minus 5. So this 2.89 times 10 to the minus 5 mole per liter is our hydroxide concentration. Now I can use that to solve for the pOH and then use that to find the pH. So negative log of 2.89 times 10 to the minus 5 gives me 4.540. This value is the pOH because I used the hydroxide concentration. So if we want to find the pH, it'll be 14 minus 4.540, which gives me a pH of 9.460. The last part of the question asks us to find the percent ionization. So what does that mean is of the total amount of my weak base, what percent of it actually reacted with the water? So what percent ionized? So just like if you had a test score, the maximum test score, for example, if it was 30, you would take what your score was and divide it by the max. So we have the actual divide by the max times 100. So the total amount of my weak base that I have is 1.50 mole per liter. If it was a strong base, 100% of that would react. So we would produce 1.5 mole per liter of hydroxide, but it's not 100%. So we can take what we actually produced and divide it by the max. So my concentration of hydroxide is 2.89 times 10 to the minus 5 divided by a maximum total of 1.5 mole per liter times 100, and we get 0.0019%. So it's actually a very small number that actually reacted with the water. Most of it just remains in this form, in the acetate ion.